class. My name is Sharice Patterson, and today I'm going to be talking about resting, local, and active potential. I was going to say transport. Please do excuse me, but potential. I hope you guys like it. So let's just go ahead and dive in. First of all, what is resting potential? It kind of is exactly what it sounds like. The neuron is resting, so it isn't doing anything. That does not mean it isn't ready to do anything, but it's just sitting there on standby. And this is where the inside of the neuron is negatively charged with respect to the outside. So that does not mean that the inside of the neuron has a negative charge. It just means that it has less than the outside of the neuron. So, for example, the sodium in the inside, so in the ICF here in the intracellular fluid, has less than potassium on the outside in the extracellular fluid, also known as the ECF. That's all it means. They both are positively charged, so please do keep that in mind, but that does not mean, that just only means that it's one less than the other. And so inside the membrane, we have a sodium and potassium pump. So as you can see here right in the center, I kind of just drew a circle and said, hey, that's our pump. And in our pump, the sodium and potassium is pumped from one side to the other. So from the outside to the inside and vice versa. And that is done by active transport. And sodium is moved inside the ICF, and I have my arrows going here to where you can see sodium is moved inside the ICF as well with the help of ATP, and the potassium is moved to the outside of the into the ECF. And so normally potassium actually moves faster. So that's just shooting out way more faster than the sodium is coming in, which then creates that imbalance, which we then would consider an electrical potential. So basically the difference from with it having a balance, so this one having more than the other, we would describe that as an electrical potential. Once at this difference or electrical potential, the ICF value is considered to have a negative 70 millivolts value. So once at that value, this means that the membrane is at a polarized state. So we would then consider it to be resting. It is now officially resting. And so how do we get out of that resting state into a local potential state? So what happens is I have my stove here. Don't worry, I'm not going to turn it on, but let's pretend that it's on. If I put my hand over the stove and it's hot, so if it's hot and it's on and I'm getting closer and closer to the stove and I can start feeling that heat, my dendrites inside senses a stimulus, or they sense that heat, which then communicates to the soma, and it's kind of like a domino effect. It communicates to the soma, down to the hillocks, down to the axons, and we'll get into that in just a bit. So once it does that, this causes a local disturbance, and the sodium gates open to where sodium ions from the ECF are now going into the ICF, and it's happening very fast. So let's go back over to our paper here. So these sodium gates here, they are now open. Once we have that disturbance, they start to open up, and I kind of have this little diagram also. So right now we were at the resting state. Once those gates opened, they'll start to open up in here. Once we reach the threshold, which is negative 55 millivolts, we would call that the local potential. So that has happened. So now we're at the local potential because now our sodium gates is open and the sodium ions are now kind of flooding into the ICF rather rapidly. And this causes the potential, as I said, to climb up more positive. So as it's climbing up that ladder there, up, this is called depolarization. So as it gets more positive, this is called the process to getting more positive is called depolarization. And once it has reached the negative 55, as I said earlier, this is what we call the threshold and local potential. Local potential is decremental, meaning that as the heat moves away, the current gets weaker. So it's going to get weaker as I move my hand further and further and further away from the stove. And so if it is hot enough and it reaches past the soma's plasma membrane and into the axon hillock, causing fast depolarization up to 35 millivolts. So past 0, now we're in the positives. We're way up here at our peak. So this is as high as we're going to go. And if it actually does get all the way up here, we would consider that to be the action potential. And so once it's at its active potential, the sodium gates automatically close. So there's no more of this. So nothing. So the sodium ions are no longer getting transported through those gates. And the potassium gates here automatically open, and they open big and fast. And it is kind of flooding the potassium back the other way into the ECF. And this is called repolarization when that happens. So when it goes here and it's coming back down, where the goal is to get back to our negative 70 millivolts. So once those potassium gates open and the potassium is flooding back into the ICF, then we are now repolarizing. So we're going way back down to the negative 70 is the goal. And so once it's reached all the way down to negative 70, we are back to our resting state. And then the sodium and potassium here, as they were moving around earlier while we were in our local potential as well as our action potential, they are now going to move back to their original state where they belong, and we are going to do it all over again once that first step is done, I guess, at local potential, when dendrites gets that stimulus or that disturbance. Thank you. I hope you guys kind of understood. I know I kind of talk fast when I am trying to explain something, but if any questions, please do reply to my discussion video. I hope this helped a lot, just kind of understanding the cycle as to what happens when, I guess, heat, pain, cold, anything kind of touches our skin. And we go from resting to local to action potential and back to resting. Thank you guys for watching. Have a good night.